Coronary artery disease is one of the leading causes of death in recent times. For regulatory approval and clinical success, the mechanical properties and the biocompatibility of the stents plays a crucial role. In medical device companies, the R&D department needs anatomically relevant data either to improve existing products or to initiate development of new products. On the other hand, clinical research departments can benefit from advanced analysis of patients for clinical trials. In this case study, we will use the coronary segmentation tool, which was designed for semi-automatic segmentation of coronary arteries on contrast-enhanced CT images. The output of the tool are masks of the coronary arteries. We will also segment the calcifications present in the coronaries and perform advanced measurements and analysis of the coronary arteries. We will finish by preparing the model for CFD simulations. First, open the coronary tool within the cardiovascular option from the segment menu. Choose the Indicate Aorta button in the coronary segmentation dialog. Choose a point on the axial images in the center of the ascending aorta at the level of the coronary ostia. You will then see a representation of part of the ascending aorta on the 3D view. Press the Add button to indicate the starting point of the left coronary artery. Choose the point in the axial images just outside of the coronary ostia. Corresponding endpoint to the left coronary can now be chosen. Select the plus icon in the S1 row. In the axial image, follow coronary branch and choose an endpoint. Indicate additional endpoints for all branches. All indicated points can be adjusted using a left click and drag. We'll repeat the process for the second coronary. The tool also allows you to separate the calcifications. However, we will do this in a separate step using the thresholding tool. When you are satisfied with the results of the coronary segmentation, choose Save Results and Save Coronaries and Calcifications. A mask will be created for each. Calculate a 3D model of the arteries and calcifications. The mask can be edited, followed by some wrapping and smoothing operations. This is the final result. For part 2, use the thresholding tool to capture the calcifications in the coronaries. We will then perform a region growing to capture only the calcium. Since the calcifications are separated, indicate several points to include all the calcifications in one mask. Choose only the main calcifications. Let's rename the mask accordingly. Calculate a 3D model of the calcifications and put the coronaries model transparent to visualize them. Check the properties of the 3D model and visualize the volume of the segmented calcifications. To perform accurate analyses of the coronaries, we will first fit a centerline into the model. Under the Analyze menu, choose the Fit Centerline tool. Highlight the coronary model and click Fit Centerline. Turn on the transparency of the 3D model to visualize the results of the centerline algorithm. Measure the length of hanging branches by choosing the Properties icon from the Analysis Objects tab in the Project Management toolbar. We can see that the centerline in the ascending aorta tends to one side. Also, the ending on one of the coronaries is very tortuous. Use the Delete Centerline Part tool to fix the aortic root. Click once in the beginning of the vessel and twice in the control point until where you want to cut. Now use the Grow segment of the centerline tool. Click on the branch you want to grow and on the center point of the vessel. Click Escape to exit the tool. For the tortuous ending, we will use the Cut Centerline Ending tool to cut this part perpendicular to the center line. Under the Measure menu, select and apply various centerline measurements to the 3D model. We will measure the best fit diameter, which is the diameter of the best fit circle at a control point, the section area, which is the area of the sectional surface normal to the center line, the minimal diameter, which is the diameter of the inscribing circle at a control point, the ellipticity, which allows the estimation of the ellipticity of a vessel at a specific point, and the distance over centerline, which allows the measurement of the distance between 2 points along the centerline. From the View menu, choose Reslice, Along Curve, select Curve. In the CPR dialog, select the coronary centerline and choose OK. You will now notice that the control points of the centerline become visible. This is how we determine the centerline section along which we will reslice the images. After the control points are selected, double-click the left mouse button. This will save the CPR view in the Reslice Objects tab of the Project Management toolbar. You can check the coronary arteries for stenosis and blockages. You can perform measurements on the resliced images, for example, the sectional area. "3D models produced in the Mimics Innovation Suite are often used in finite element analysis and computational fluid dynamics applications for research studies. The FEA module in 3Matic can be used to prepare and pre-process the surface and volume geometry of these 3D models in order to prepare them to be used in many solver packages like Fluent, ANSYS, Abacus, among others. In this exercise, an aorta coronaries model is prepared with a surface and volume meshing to be processed for use in the ANSYS software. First, select the model from the 3D objects list and press the Remesh button. This will open 3Matic with the selected object loaded in the work area. Rename the model to coronaries. Duplicate the 3D object of the coronaries and hide the duplicated object. Go to the Mark toolbar and select the Smooth Region tool. Left-click on one of the outlet of the aorta to mark this region. Right-click on the marked area and select Separate, Move to Surface, Create New. All surfaces that appear in the scene tree are written as surface sets in the mesh file during export. Hence, you can use this feature to already identify boundary regions for conducting your simulations later on. Under the Remesh menu, choose the Create Inspection Scene tool to check the quality of the triangles. Set the shape measure to skewness, the current measure to shape measure, and the minimum value to 0 and the maximum value to 0.3. The chosen settings determine the number of low-quality triangles. You can see that the 3D object is composed of a large number of triangles. The reduce operation can be used to reduce the number of triangles in the 3D object. In the Fix menu, select the Reduce tool and click Apply. The histogram is updated after the triangle reduction operation. Despite the higher percentage of low-quality triangles, the total number of triangles has been significantly reduced. We want to obtain different triangle sizes for the coronary arteries and for the aorta respectively. In order to do that, we will mark triangles to identify different regions. In the Mark menu, select the Wave Brush Mark tool. Adjust the brush diameter in the Operations tab if necessary, and press the Shift key to mark triangles all through the coronaries. Use the Auto Remesh tool under the Remesh menu to optimize the triangles of the part. Use Skewness as shape measure and set a shape quality threshold of 0.3. For geometrical error, use 0.1 millimeters. Define 0.1 millimeters for the minimum triangle edge length and 2.0 millimeters for the maximum triangle edge length. In the local remesh parameters, select the marked triangles as entity and define the maximum edge length as 0.8 millimeters and the influence area as 1 millimeter. Finally, press the Add button and define a growth rate of 20% before clicking Apply. Use the Optimize Triangle elements to create a volume mesh. Use the Create Volume Mesh under the Remesh menu to create a volume mesh with a maximum edge length of 2 millimeters. In order to visualize the volume elements, go back to the Work Area tab and create a section to clip the 3D object. In the Properties tab, toggle the Clip checkbox and change the position values as needed. The toggle checkbox is used to flip the direction that the section is viewed from. Export the mesh to the Fluent format by going to the File menu, then selecting Export Fluent. Add the mesh to the output window and choose a directory. You can also export the mesh to other FEA and CFD formats.